Okay, so I'll tell you a bit about our recent progress on planning chemical reactions and predicting them. So before we get to the technical content of the talk, I just have to really quickly tell you what the problem is and why do we care about it. So this might be already familiar to you if you managed to wake up for Staszek's talk today morning. So synthesis is essentially a problem of cooking, but with molecules. So if you ever cooked something sufficiently difficult that you needed to use a recipe, you're probably familiar. So you would have a recipe when you start with some materials that you buy at the grocery store, for example, and then you would have a sequence of steps that use those materials or some intermediates that you've obtained in previous steps, and then you obtain whatever you wanted to get cook at the end. So chemical synthesis is the same, but with molecules. So you would have some starting molecules that you buy at a grocery store for molecules, which are companies that have a large catalog of things that you can order. And then you would run steps, which in this case are chemical reactions, building more complex stuff, and at the end, ending up with what you wanted to have. And so the problem of synthesis planning, if you formalize it as a sort of input-output ML kind of problem, your input would be the set of building blocks, so the things that you can order, and also a target molecule, which is the more complex molecule that you want to end up with. And then your output would be the synthesis route, which is a tree of molecules where all the leaves are in the building block set. The root is the target molecule that you want to have, and all the intermediate nodes correspond to reactions that make sense. And we'll get in a little while what making sense means in this context. So now you know the problem. Why do we care about it? So synthesis shows up in various domains of science. The one we care about most here is drug discovery. So if you're a pharma company, like our partner Novartis, then if you want to design a new drug, you operate in this design, make, test cycle. So design pertains to coming up with an idea of a molecule on paper, if you will. So you'll try to come up with an idea that maximizes some sort of utility. It has some sort of properties or predicted properties that you think you want. And then once you have an idea, you would go and try to make it in the lab. So you would come up with this recipe that gets you to that molecule. And once you get your hands on it, you would test it in the lab, hopefully see you have the properties that you wanted. And then you would go around optimizing things. Hopefully you end up with something useful. You can plug in machine learning in various places of this pipeline. The design part, I won't tell you much about. This is something that we've done in our team a few years back, so you can take a look at this paper. Just one thing to note, so we've made this generative model a few years back, and actually it has been used at Novartis since then with a lot of success, so these things work. But then it's seeing this cycle, it might be kind of obvious why after doing some progress on the design part, we decided to look into synthesis. And the reason is that it often ends up being a bottleneck. So often you come up with something, either a chemist or a model comes up with something, and then you're just not able to find a recipe for it, and then it's essentially useless. And this also explains this little pun from the title of the talk, fake it till you make it. The molecules that you come up during design, they're essentially fake, maybe fancy ideas, but they're essentially useless until you can actually make them. So hopefully that explains why you need to be good at finding synthesis paths. And then if you want to tackle synthesis, it's usually in this split into these two parts. One part is reaction prediction. So given a molecule, predict a reaction that would give me that molecule in a single step. And this is what I will tell you about specifically, about the specific recent results that we got on that side. And just to mention, if you have this model, that essentially becomes your environment in which you're doing search. So then you have a search problem where you start with what you want to get. And by the way, that's why it's called retrosynthesis, because you're going backwards from what you want to obtain. And then you would call your model on the molecule you want. It gives you some reactions. Then you choose one of those reactions that requires some reactants. Some of them maybe are in your building block set, then you're done. And those that aren't, you'd have to call your model again and so on. So hopefully that's clear how we could do search in this setup. And again, I won't tell you much about search here, just to focus on one thing. The talk isn't so long. Give you another reference. So we've done some work on search as well, and in fact, this little pointer is a maybe nice overview of things in this area. So a nice entry point if you're curious to get interested, and also there's a open source library that comes with that. But as I said, here I will focus on this left part, so predicting the chemical reactions. Hopefully it makes sense that it's a prerequisite of making anything useful. If your reaction model is bad, then you're essentially then you're doing search under a flawed environment, and that can't work, right? And so we'll focus on this here, so predicting chemical reactions. And in particular, I will tell you about our most recent results. The results are so recent that they aren't yet on archive. They will probably be in a week or so, so we're getting a bit of early access to that. And in particular, I will tell you about our results, so how we went about it, what kind of progress we made. And then I think at the end, there will be also something that's maybe a bit more wildly applicable beyond just synthesis. So if you look at how this problem is approached in general, there are maybe two very different angles that people usually take. One is this sort of deep learning end-to-end kind of style, when you're just saying, I'm going to just cram it through an end-to-end transformer and learn it end-to-end. And the other approach is much more symbolic and much more constrained, which essentially notices that if you overlay the reactance graphs and the product graphs, usually not many things change. So you can think of predicting maybe just a set of bonds that change between one and the other, and that constrains things quite a lot. So in our project, we figure, okay, we'll just try both, right? We just try either of these directions. We see what's the state of the art there. We see how far we can push it. So I'll tell you a bit about what we've done on both, so how we managed to push the state of the art a little bit on both directions. But then also, more excitingly, how we managed to then get it all back together again. So we managed to get something that sort of combines those two, and I think that's the most maybe interesting part and something that hasn't been done in the field before, I think. So on the end-to-end side, things are pretty simple if you're doing things end-to-end. You just need a way to tokenize your input, so your molecule, you want to turn it into a sequence. There are sort of well-known approaches in cheminformatics, which sort of linearize a graph into the Smiles notation, essentially a depth-first search. And then you can just put it through an encoder-decoder transformer, which then encodes your input, so your product, and decodes the representations for your reactants. And then you parse those back into graphs, and you get some model out of that. And then there are some tricks on top that I won't tell you about. You can do things with data augmentation, for example, because Smiles are generally not a unique representation of graphs, so you can do things in that direction. But essentially, that simple transformer is sort of state-of-the-art, depends how you measure things. If you benchmark it on a particular data set, you get results kind of like this on this curve. The K on the x-axis essentially means how many outputs the model is allowed to produce. So if you ask for more possible reactions, there's just a larger chance that you will encounter the one that was actually as ground truth in your data set. So things look kind of reasonable. So on that end, if you're going end-to-end, you can just tweak the architecture a little bit. So we did try that. You do get a little bit better if you just throw newer LLM tricks at it. If you add things like grouped query attention, better norm, better activations, things like this. So that's kind of useful. So then we figured, okay, what can we do on the symbolic side, right? How can we surpass this? So on the symbolic models, the way people go about it, it starts similar. You still need a way of encoding your molecules. And it could be also a transformer encoder on Smiles. But more commonly, and in our case, we use the graph neural net encoder. And it will become more obvious later how that's beneficial in our case. But after you encode your molecule, if you want to go symbolic, you're not going to just predict the output graph. You're going to predict the diff, right? And the way this is done is essentially you look at your reactions in your training set, and then you would extract all the possible patterns of how the product changes to reactants. You can think of diffing the graphs, kind of seeing what changes. And then once you extract those patterns from your training data, maybe you have like 100K patterns of these bond changes, then suddenly predicting the reactants is no longer a generative problem. It becomes a big classification problem when you have 100K classes. You're trying to pick the right transformation. And then if you pick the right one, it's a deterministic process of how you apply it and get the reactance graph. So that's kind of a off-the-shelf approach how you would do it in a symbolic way. And this is perhaps even the most common in the industry, just because it's very fast and very, very quick to run, because it's no longer autoaggressive. You just do classification on a large pool of transformations, or just go from there. So if you apply it kind of out of the box, it does reasonably. It doesn't reach what you get from transformers. So I thought, okay, how can we prove this, right? What's going wrong with this? So one weakness that you can notice in this kind of models is that essentially they treat all of these templates, all of these classes, as just classes 1, 2, 3, and so on, and trying to pick between them. So it kind of loses the fact that these templates underneath aren't just template 1, template 2, but they have structure, right? They are underneath this complex sort of bipartite graphs saying this subgraph is changing into this subgraph, right? And you're completely ignoring that. And because you're ignoring that, you run into a problem of rare templates. So some of the templates will just occur in maybe just 2 or 3 reactions, and the model will then struggle to learn that, right? So one trick that we started with is, okay, instead of just having an encoder for your product and then doing classification, you will just have a class encoder as well. So you can encode your template as well, and then it's more of a contrastive learning problem when you're trying to pair the products into the right templates. And now suddenly you break out of this problem of some templates being rare because maybe a template is rare, but it's similar to other templates. You can sort of do transfer learning across templates. Of course, getting that to work requires you to be able to encode the template, so then you have to think, well, a template is kind of just like 2 graphs with a matching between them. So if you squint a little bit, you turn it into a graph, then you can pass it through a GNN and can encode it that way. And then, so that addresses one of the problems with these kinds of models. The other problem is that I told you that when you choose a template, it's deterministic to apply it and get the right outcome. It's sort of true, but also sort of isn't. So it's deterministic, but you might get multiple outputs if you do this. Because if you think about applying a template, it's kind of looking up the subgraph in your input molecule and then rewiring that subgraph into some other subgraph. So if it occurs several times, you get several outcomes. And in fact, this is something that happens in these kinds of models. You get the model, even if it chooses the right template, it might give you 4 outcomes as a final result, and then it doesn't know how to rank them. So then the other question is, can you easily modify this so that you not only predict which transformation to pick, but also how you apply it? And then this is where we get back to the fact that we used a GNN. So we not only have a representation for the entire product or the entire template, but also representations on the atom level. So for the nodes in the input molecule and for the nodes in the template. So what you can do is you can essentially add a separate loss. You can have we call it a localization loss. It's sort of a matching loss, if you will, that takes all the representations of the left-hand side of your template and representations of your input molecule, and then tries to learn to match the atoms together. So it essentially tries to learn which nodes in the left-hand side of the template match where in the graph. And that allows you to essentially, instead of blindly applying the template everywhere, just learn where to apply it. And you get it sort of for free. It's a very small addition to the network because you have all of those atom-level representations anyway. And so if you do like this, you remove these 2 maybe hurdles from these models, and you can actually get pretty close to what you get from this end-to-end transformer, but you don't surpass it. So you could say, okay, we've tried both, and the transformer has won in the end, so end-to-end deep learning has triumphed, and I guess we all go use that. But it's a bit too simplistic, and if you look at this curve, it might seem like one model is just better than the other. But if you look under the hood and, for example, you split your testing data set based on how similar those reactions are to your training data, and here, similarity I measure as essentially frequency of that template in training data. So of course, if you have things that are more similar to your training data, your models generally do better at it. But what you find is that if you compare the 2 models, it's not really such a clear picture anymore. So you see that if you have something that's very far from the training data, so in fact, there might be cases when the template that you would need to get the right answer didn't exist in training data, then the template-based model has no chances of succeeding. So on one end, if it's very extrapolative, you only can use this sort of unconstrained transformer model because the template-based model is too constrained to get it. And then, interestingly, if it's similar enough to the training data that there are tons of similar examples, then the transformer also wins. But then we see that in the middle, when you have only a handful of examples, somehow the symbolic model is able to pick that out better and learn from maybe 2, 3, or 5 similar examples in the training set. So if you look at it like this, you see it's sort of not a clear cut of one being better. So then you ask the question of if we can get the best of both worlds somehow. And this is how we get to our model from the paper that isn't out yet. So we call it a chimera for obvious reasons because it has 2 very different parts to it. So how would you combine things, right? How would you get an input, you get some reactions from the 2 models. The idea is that you can't really combine those 2 models in some sort of probability space because, well, the transformer thinks of token probabilities, the other model thinks of template probabilities, it doesn't really match. But you can combine them in an output space, right? You can look at the reactions predicted by one and the other, and you can try to find co-occurrences, right? Intuitively, a reaction that is ranked highly by both models should be maybe ranked even highly if you try to combine things. Whereas a reaction that's ranked highly only by one of the models, maybe you should discount that a little bit. And that's a useful intuition, and you can formalize it if you think of essentially, well, I know I want to combine things somehow, but I don't know how to weigh one model versus the other. I'm not sure how to weigh the first prediction versus the second. But what you can do is essentially you can introduce these weights that tell you how you trust the predictions from different models and predictions of different ranks. And then you can formulate a learning to rank loss on top of that. You take your validation set, you optimize that, and you basically get an optimal way of combining the 2 models. And what we see is quite strikingly, you get something much better than either. Even though from this original curves, it would seem that, well, the models are kind of close, one of them is slightly better. They seem to be doing very different things. And if you just learn to combine them on a validation set, and the extra stuff that you add is, I think, like a 200 numbers, so it's not really, you're not adding much. But just by learning how to simply combine them, you get something much better than both, and also something much better across this entire spectrum of sort of weird versus less weird reactions. And I think that's maybe a nice part of the story, and maybe something that's a bit more maybe generalizable. If you have 2 approaches and 2 models, one of them seems slightly better. I think the question is, are they 2 tweaks to the same transformer architecture? Maybe then one is indeed slightly better and that's the end. Or maybe they are diverse enough that they are somehow making completely different errors or thinking in completely different ways. And then maybe you can cheaply find a way to combine them. That's maybe one lesson to take away from that. And then I have skipped a lot of content, of course. If the paper is out on arXiv in a few weeks, you can take a look. But as I said, just to tie it back to what I said at the beginning, so we have a better model for predicting the single-step reactions. So what you can do with it is now you can go and run search. And this is something we do in the paper as well. So we try to run search for relatively complex molecules. We find that we can find nice complex routes. That's one example on the left. And then just to throw some acknowledgements, so obviously this is not just me. So this is all work that has been done by both my colleagues at MSR, some students that we encountered, and also our colleagues at our partner company, Novartis. And then I think we're near the end, so we'll open up for questions. So the last thing from me is, as I said, I'm from this AI for Science team at Microsoft Research. It's a pretty big-ish initiative now, 130 people on 3 continents, I believe. So yeah, we're going strong. We're doing a lot of things with drug discovery, materials, proteins, simulating climate, and so on. So if you're interested in that, there's a link. You can read more, or you can just find me somewhere and hit me up. Yeah, and I think that's my 20 minutes, so we can open for questions.